I'm going to talk about greenhouse gas emission reduction. First, I'm going to talk about emissions, where they come from, where they're going to, and technical options to reduce those emissions. Then I'm going to talk about the costs of greenhouse gas emission reduction. And finally, I'm going to talk about policy instruments for greenhouse gas emission reduction. This is part one of a three-part series on the economics of climate change, starting with emission reduction. Then there is a part on the impact of climate change, and finally there is a part on climate policy. But let's start with emissions and where they're coming from. There's three main anthropogenic greenhouse gases. It's carbon dioxide, CO2, that's methane, CH4, and that's nitrous oxide, N2O. And as you can see in the pie chart, CO2 is by far the most important of these greenhouse gases, making up roughly 75% of the total greenhouse gas emissions in the recent past. 36% comes from the generation of power and heat, 15% from manufacturing, and another 15% from transport. And as these titles suggest, this comes from the combustion of fossil fuels. So how does this work? From an economic perspective, CO2 emissions are an externality, an unintended and uncompensated byproduct of the actions of one economic agent, say a power generator, on everybody else, on other economic agents. From a physical or chemical perspective, it's not an externality at all. So what do you do when you burn fossil fuels? Well, let's take a lump of coal. Coal is a carbohydrate, that is, it consists of carbon atoms and hydrogen atoms, and the first thing you do is you add heat, you add energy. And that energy breaks the chemical bonds between the carbon and the hydrates. It breaks the carbohydrates into three atoms of carbon and hydrogen. Then you add oxygen, you oxidize the whole thing, and the oxygen combines with the carbon to form CO2. That's dumped into the atmosphere, and the hydrogen atoms oxidize, form a new chemical bond with the oxygen to make H2O, and that's also water vapor, and that's also dumped into the atmosphere, and that's sort of the clouds of steam that you see come out of power plants. CO2 is of course transparent. Now it's in the formation of the new chemical bonds between the C and the O, and between the H and the O, and that is where the energy comes from. You add energy to break the chemical bonds, but then you oxidize the thing and you form new chemical bonds, and that is how energy is released. So from this perspective, it is intrinsic. The formation of CO2 is intrinsic to the process of getting energy out of fossil fuels. So you simply cannot burn fossil fuels, or you cannot get energy out of fossil fuels without making CO2. That's an important thing to keep in mind. This is not a waste product. If you compare it, say, to sulfur emissions, SO2, that's also an externality from an economic perspective. It's a nuisance from an environmental perspective because it does damage, it causes acid rain, it damages forests, it kills fish. And from a chemical perspective, if you're running a power plant, you actually do not want to do this, because the sulfur in your coal or the sulfur in your oil actually makes your machines run less efficiently. So nobody wants SO2, but not CO2. You absolutely must make CO2 if you want to get your energy out of your fossil fuels. So that is the first thing to keep in mind here. This is by far the most important source of greenhouse gases and of carbon dioxide. Another source of carbon dioxide, roughly 20%, is land use change. So how does this work? Essentially what we've been doing for a long while now is replace forest with grassland and grassland with cropland. And essentially trees are also made of carbohydrate, grass is also made of carbohydrate, but essentially what you do is you replace something big, something that is full of carbohydrates with something small, and the excess you need to get rid of. Sometimes the trees are left to rot, but more often the trees are burned, and in that way CO2 is released into the atmosphere. A much smaller source of carbon dioxide emissions is cement production. That's 2 or 3% worldwide. Again, this is intrinsic to the process. What you do is you take limestone, you add heat to drive out the excess CO2 or the excess carbon, and then the limestone is chemically transformed into cement. And again, there's no way to avoid the formation of CO2 in this process. So that is where our carbon dioxide comes from. Methane is the second most important greenhouse gas, roughly 17–20% of the total of greenhouse gases. Where does methane comes from? It comes from various sources. One important source are ruminants, that's cows essentially, and similar animals. Now, what do these animals do? Well, essentially they transform grass, because that's mostly what they eat, and some herbs, but mostly grass, and they transform that into milk, one of the products that we use, and meat, another product that we get out of our livestock. If you compare the chemical balances of the grass that goes in and the milk that comes out, you would find that there is too much hydrogen. Somehow in that process, hydrogen has gone missing. Grass is a carbohydrate, cows are mostly carbohydrates, and a lot of water. And milk is also carbohydrate, meat is also a carbohydrate, right? But they're all different carbohydrates, and somehow there's a lot of hydrogen that disappeared. Where did it disappear to? So what do cows do? Essentially, they eat grass, they turn it into other organic products, meat and muscle and that sort of stuff, but they need to get rid of the hydrogen. And they do that in their stomach. Now, hydrogen is a dangerous thing. If you have free-floating hydrogen in an oxygen-rich environment, it goes to OH, a hydrogen radical, and they are extremely reactive. They essentially destroy everything. They react with everything and erode everything. Stomachs are oxygen-poor environments, so that is not the main risk. But then the hydrogen goes to H2, goes to hydrogen atoms, go to hydrogen gas. And then essentially that is the stuff that makes zeppelins float. So that is not something you want in your tummy either. So what have cows done, or rather their ancestors millions of years ago, they formed a symbiotic relationship with methanogenic bacteria. Essentially what these bacteria do is they sacrifice one useful carbon atom to get rid of 4 damaging hydrogen atoms. They form CH4, and then the cow burps that out. Again, this is intrinsic to the transformation of grass into milk and meat. You need to get rid of the hydrogen somehow. It's a bit unclear how you would solve this. There are animals that have the same ecological function and occupy the same ecological niche as cattle do, and that's the kangaroo. The kangaroo does not emit CH4, but instead does not burp out CH4, but instead poops out acetate, which is another way of getting rid of the excess hydrogen. But of course, then you immediately understand that in order to get cows to behave like kangaroos, you need to re-engineer the metabolism. And these animals have separated a long, long time ago. There is some talk that with particular food supplements, you can reduce the CH4 emission from cows, but it's not much more than a reduction. You can't really avoid it. So that is a big source of methane. And again, it is intrinsic to the process. The second main source of methane are paddy rice and waste. Paddy rice is essentially wet rice. So rice is a plant. It leaves die off, and when it leaves fall, they fall into the water. And if plant material rots in an oxygen-rich environment, it goes to carbon dioxide. But underwater, you're starved of oxygen, so you're in an oxygen-poor environment. And then rotting means that you go to not CO2, which requires oxygen, but CH4. It goes to methane that then bubbles up out of the rice fields. This is hard to avoid, very hard to avoid, and the obvious solution is to go from wet rice to dry rice. The problem with dry rice is that it's so far less productive than wet rice. If you want to get a lot of calories out of a plot of land and you're in the tropics, then you want to grow rice. It's simply the most productive grain crop that we know. Waste is a very similar process as the paddy rice. We throw away lots of stuff, including lots of organic stuff, wasted food and that sort of stuff. And that organic stuff rots, but it's thrown typically into a landfill, and in a landfill there's other waste on top of it, so there's not a lot of oxygen in the landfill, and that means that organic material that you threw in the bin has no other option but to rot towards CH4, towards methane, and that then gets leaked into the atmosphere as well. The final source of methane, a significant source of methane, is leakage. Methane is CH4, and that is what we call it if it's a nuisance, if we don't want it. If we have CH4 that we do like, then we call it natural gas. Chemically, the two are just identical. The issue with natural gas is that it's found in one place, used in another place, so it's transported. And the pipes that transport natural gas are not airtight, and some of the natural gas escapes. And if it's in the pipe, it's called natural gas, and if it escapes into the atmosphere, it's called methane. So that is an important source of methane. Another thing important there is that gas is often found together with oil, and gas, if it's found in significant quantities with oil, is typically burned. That's the flaring that you see in oil fields. With smaller quantities, it's simply vented into the atmosphere. And with coal, it's typically not vented at all. It's just vented into the atmosphere. So that is where the methane comes from. The third most important anthropogenic greenhouse gas is nitrous oxide, N2O, and this essentially comes from the over-application of fertilizers in agriculture. And the reason that farmers use more fertilizers than they need strictly is because fertilizers are cheap. A bad harvest is very expensive, so any risk-averse farmer would overuse fertilizer, and whatever fertilizer is put on the field that the plants don't need is simply washed away, gets into the soil, and is then chemically transformed into nitrous oxide and a range of other substances. Again, it is very hard to get rid of this because the price you would pay is failed harvests. And then there's a whole swath of other greenhouse gases, particularly the fluorocarbons and SF6. They are essentially very powerful greenhouse gases that we use in very small quantities, but because they are so powerful, they are important nonetheless. And they have very specialized uses in industry. These things don't occur naturally. but they are used as solvents, they are used as propellants, and so on and so forth. They have very niche, particular niche applications in certain industries.